So after my previous class of 721 ended, I was in my office, did usual post-processing for that class, getting things uploaded to Canvas, YouTube, etc. And once all that was done, I had 4 minutes left until time for this class. And at that point, I had mentioned to you earlier, Walker, that I had not know what I was going to cover today. And when.
Wait, you said. Oh, never mind.
Yeah.
Mentioned.
Yeah. In our meeting, that I didn't know what I was going to cover today. And so then with 4 minutes to go, I was like, I still don't know what I'm going to cover today. I did think of something. I'm not sure how much I can do with it, but it is a natural continuation of things that I have been covering. So figure, what the hey. Oh, this is one of the bad pieces of chalk. I hate that. Yeah, but there's a certain piece of chalk that you tell me as soon as you start writing, you can't really write smoothly. So. Bye. Let's see what else we got here. I think it's much better. Better, I guess, but still not great. Okay. All right. Now, I was talking about. I'm going to go to my office and grab a good one. Okay. All right. So far, spending a lot of time on systems of ODEs of this form, y prime equals ay, and the matrix A, and it may not have been as clear as much as I should have, but it's always going to be a constant matrix. In other words, independent of T. So all the solution formulas that have been derived to this point have come from that, have rested on that assumption. All right. And the thing is, which it makes sense because the main objective is to come up with solution formulas for higher order scalar ODEs where the coefficients have been assumed constant, the coefficients P and Q. But what happens if we drop that assumption of being a constant matrix? Okay, sorry. All right. So this kind of system of ODEs is an example of an autonomous system. So in general, an autonomous system of ODEs is a system of ODEs that has this form, where the right-hand side can be described, so you have y prime on the left side, and the right side can be described as a function of only y, as in not t. Now, now, of course, the right-hand side, you can argue that implicitly depends on t, just because y depends on t. but that's the only time dependence allowed. There's no other dependence of f on t. So if it's possible to describe it this way, it's autonomous. And certainly that's what we have here. Your right-hand side is nothing more than a times y. Okay, so what if the system is non-autonomous? So that would be something in this form: y prime is equal to some function f of t and y. So there's not only the dependence on t through y, but also t popping up in other respects. And we'll still focus on the linear case. Y prime is a matrix A of t times y. So what can we do there in terms of a solution formula? All right. Okay, so now in the constant A case, we have a solution formula: y of t equals e to the at y of 0. So is there a way to generalize this solution formula to the case of a matrix A of t? Now, there is some guidance for this, because we do know what to do in the case where we only have one ODE. So A is a 1-by-1 matrix, it's just a number. So if I try to do a most straightforward generalization of that to a matrix case, then I'm proposing a solution formula. And though my question marks, none of this is for sure, but it will be investigated. So it could be something like this: e to the integral from 0 to t of a of s ds times y of 0. So that's the question: does it really work that way? So this is yes if A is 1-by-1. And it's been a while since I've looked at this. So I believe the answer is that no, this does not generalize to the case of a matrix, that we can't do this. But I'm just going to go ahead and try it. See if this really does satisfy the system ODEs. So the question to ask is the derivative of this exponential equal to A of t times itself? Okay. So if we can verify that, then yes, this is a valid solution formula. Because that's what I need to, I'm saying this is the solution, so I take the derivative of it, and I should get A of t times the same exponential times y0. In other words, A of t times the solution itself. Therefore, it would satisfy that. So, does that happen? So to find out, we will express this exponential as a Taylor series. So we have sum of the integral raised to the jth power over j factorial. All right. So then what I'll do is I'll write out the first few terms. So for j equals 0, we're just going to have identity. And then for the next term, we'll just have the integral itself. And then we'll have 1/2 times this integral whole thing squared, and so on. Okay. Questions up to this point? All right. So if I take the derivative of this with respect to t, then what I should get are the first terms again times a of t for this whole thing to work. So let's see what happens. So derivative, all right, well first we have identity, so derivative that's 0. And then the derivative of this is just going to be, by fundamental theorem of calculus, you take the limit and plug it into the integrand, so it's just a of t, which is the first term times a of t, so go us. So far so good. And now we go over here. So in this case, we have a matrix squared that we got to take the derivative of. And for that, we use the, we have to use the product rule. And okay, and you might think, oh, well, shouldn't we just use the power rule? And it turns out there's a little bit of a problem with that. Okay, actually I had time, so I'm going to show you what the power rule is, not a power, product rule is for matrices. So suppose you have a matrix product, A of t, B of t, and you want to look at the ij entry, take the derivative. So now what I'll do is I'll write out the ij entry of this product. So that would give us aik of t, bkj of t. And we take a derivative of all that. So then we got to use a product rule on each term. So that would be sum aik prime bkj, and then another sum aik bkj prime. All right. Well, just as this is a matrix product, you see the index pattern doesn't change. These are also matrix products. So the derivative of a of t times b of t, what matrix products should I write here? We have two of them because it's product rule. So what matrix products do we have represented by these summations.
You said what matrix product?
Yeah, like here, this matrix product gave us this.
Okay.
Here we have similar expressions that represent products of which matrices?
A I K.
Well, notice the index. Okay, A of t, B of t led to this, where the indices has come from the matrix multiplication formula. But now what we have here are, because I took a derivative of all of this, we have derivatives down here. So these, each of these is also a matrix product, because again, notice the index patterns are the same.
Okay.
So it's just that here we're multiplying different matrices than we are here. So what matrices would that be? So what I want to put in the square brackets is an expression kind of like this. But it's not going to be A of t, B of t.
Right.
Because we took the derivative.
A prime T. B prime T. No, well, B of T.
Yes.
And then we do plus, and then switch it. So A of T, B prime of T.
Yeah. Now, this is exactly what you'd expect from a product rule, but there's one key difference when it comes to matrices. Because with a scalar function, you say, okay, f times g prime is equal to f prime g plus g prime f, or you can rearrange the order in each term whichever you want because multiplication is commutative, but not for matrices. In each term, the A or A prime must come before the B or the B prime. You have to, so whatever order of matrices are multiplied in here has to be preserved in here.
Okay.
So what that means is the power rule does not hold with matrices. If A and B were equal, so I'd be taking a derivative of A squared, I would not get 2A, A prime, I would get A prime A plus A prime. You cannot combine the like terms because you don't have like terms anymore.
Yeah, so I'm just trying to remember. I know it's silly, probably, but in general, matrix multiplication is not.
Yeah, matrix multiplication is not commutative.
Commutative. Okay, that's what I was trying to getting out of that. Okay.
Yeah,
yeah.
So because I cannot switch these or these, we do not have a power rule for differentiating
Yeah,
matrices.
I guess that does make sense. Sorry, I had to think of it with okay.
Yeah, so now when I go to take a derivative of this term, what I'll get is 1/2. Oh, okay, this spells product out here. And I have the integral times its derivative, which is A of t, plus A of t times the integral. And so on. Which is not equal to just A of t times the integral, which is what I needed for a solution of this system of ODEs. So we do not have a match. So therefore, this solution formula is just plain wrong. So that's unfortunate. That everything just kind of falls apart. That dang matrix lack of commutativity of matrix multiplication. Okay. So since that didn't work, is there something else coming up? And the answer is maybe. Okay. So I'll make it another attempt, and I'll probably do it for the rest of the class time, and I'll be good. Oh, that reminds me, I'll make sure that I've told everybody. So we will not have class Thursday. I think I might have said that, but just making sure. Because I'll be driving to Starkville at the time to give a talk at Mississippi State on Friday. We will also not have class next Thursday, the 11th, because I'm substituting for someone else in that time. A little emergency situation. So we don't have any class meetings left. Okay, so we'll have Tuesday, which is, okay, so November 9th, November 16th. I'll think about November 23rd if I was right before Thanksgiving break. And then, so 3 Tuesdays, and then there's the last week of class. And considering it had difficulty deciding what to cover today, that difficulty will continue. But at least I'll have time to think about it before next class. Okay, so here's what we can do. We can convert to our non-autonomous system to an autonomous one. And the way you do that is you add on an extra equation. So here's our system as we had it, and now I add on another equation, which is just t prime is equal to 1. So you make your t variable, which is originally just an independent variable, now it's a dependent variable. And then the initial condition, before we had y0 is y0, given initial condition, and then t of 0 is 0. So you solve that system ODEs and t is just t. But now, because t is now part of your solution, this right-hand side depends only on variables that are featured here. So this system meets the definition of autonomous. So now I'm thinking, well, since this is autonomous, maybe we could, so now we have this, like maybe I can do a matrix exponential or something like before, except I just realized there's still a problem. It may be autonomous, but it's nonlinear now. The idea of using a matrix exponential to describe the solution rested on 2 assumptions. One, that the system was autonomous, and 2, that the system was linear. So we have to choose between linear and autonomous when the matrix depends on t. We can't have both anymore. So now what? God blows, to be honest. Sorry. So let's see what we can do. I might have done something like this before, but I'm not sure. But in case I want to make sure that I have done it. Okay. So in general, if I find a new dependent variable, I'll call it z, to contain all the dependent variables, so y and t. So now I have z prime equals a function of z, which just includes all of this. So although f is a nonlinear function of a variable z, in other words, the variables y and t, I can try to linearize it. So at least I can break f down into a linear part and a nonlinear part. So I want to write it as jz plus some function n of z. So j is called the Jacobian matrix, or also the Jacobian of f. F is a vector valued function. And therefore, this is linear. So this is a linear part. And what's left is the nonlinear part. Okay. So if I can break it down this way, that would be nice. Now, how do I do that? A Jacobian matrix, this actually comes up in multivariable calculus. It's basically a form of derivative for multivariables. What you're doing is you're taking a derivative of each component of your function, your vector valued function, because this is component functions. You take a first partial derivative of each component function with respect to each of the variables. So each of the y's and the t's, or just t. So a Jacobian is going to be the partial derivative of the first part of f with respect to the all the y's. This is I'm going to use a 2x2 block structure because we have our unknowns broken down into two components, y and t. This block here will be the derivative of the same thing with respect to t. Now I want to emphasize, this is a matrix. We're taking derivative with respect to a vector. Really what we're doing, this is a matrix. Each entry of a matrix is a partial derivative of this expression with respect to like one component of this expression with respect to one of the y's. This right here is a vector, column vector, because a of ty is a column vector. We're taking a derivative of each component of that with respect to t. That's what goes here. So this is n by 1. Then, what goes down here, derivatives of the other component. Derivative of 1 with respect to y, and a derivative of 1 with respect to t. Of course, both of those are 0. All right. So this is 1 by n, and this is 1 by 1. So the Jacobian matrix as a whole is n plus 1 rows, n plus 1 columns, because you have n plus 1 unknowns. The whole vector y and then t. So now, if you actually take the derivatives, when you take a derivative of a matrix vector product with respect to the vector, what do you get to the matrix? So it's just A of t. Here, if I were taking derivative with respect to t, so that's going to be a prime of t, which is a matrix, times y, which is a vector. So this is a vector. And then, as I said earlier, down below, you just have 0. Actually, I'm going to write this 0 as 0 of a vector transpose, which sounds odd, but I'm doing that because by convention, vectors are column vectors, and this is a row vector. So you have the whole last row is zeros. Okay. So now we have a Jacobian matrix. So this is the linear part of this system of ODEs. And then the nonlinear part, we take the easy way out on defining that. All it is f minus jz. So it's everything else in f. You actually could think of it as a Taylor remainder, because it really is equal to that. I know I've been doing some weird things up here. Questions about any of it? If you're able to break down your system of ODEs into the sum of a linear part and nonlinear part, you can get at least a solution formula. Because now what you can do is I can rearrange it. Z prime minus JZ is equal to MC. And this is you can think of it as a system of linear ODEs, except with a nonlinear source term. But we're going to treat this as a source term, even though it really isn't technically, because it depends on Z. But then what I can still do with this is use what we've seen in other situations, an integrating factor. I can multiply both sides of this by e to the minus jz. Get my vector symbols. Okay. And now I can do the same as in other situations where I have an integrating factor. I can integrate both sides from like 0 to t, and I get oh, I forgot to see prime here. Okay. All right. So that's terribly written. Sorry. E to the minus jz z prime minus all that. Okay. So I can so this results from a product rule where everything works out like you want it to, because the matrix J is a oh shoot, I'd be careful about this. I'm sorry. Dang it. Okay. I'm going to find Jn to be this Jacobian matrix, but evaluated at a specific time n. So A of Tn, A prime of Tn, Yn, 0, 0. All right, I have to do it. J has to be a constant matrix here. So these need to be Jn's. Otherwise, I have the same pitfalls that I mentioned earlier. Sorry, I totally messed this up. Okay, this part's okay. All right. My integrating factor is supposed to be e to the jnt, not z. Now it's as it should be. Do I even have any time left at all? 5 minutes. Okay. Now I can integrate. I get, I'll sketch my case here before I screw up anything else. Z of t is equal to okay, Z of, let's do this way, make like a single time set. Z of tn plus 1 equals Z of tn. So I'm actually going to integrate from time tn to time tn plus 1. If I get around to writing up these notes, which I know I've been negligent on lately, I will write it out fully. So what I'm doing here is integrating both sides from time tn, the time where I evaluated the Jacobian, to tn plus 1. And what I will get is Zn plus 1 is e to the jn delta t, Z of tn. Okay. What? Oh, sorry, I just saw something in the chat here. Oh, okay. So Caitlin had to leave. All right. Plus integral from 0, so from tn to tn plus 1, e to the jn delta t minus s. No. Tn plus 1 minus s. N, capital N, of Z of s ds. Okay. So we have a solution formula that resembles solution formulas that we've seen before for ODEs that have source terms. And this is going to be used as a starting point for a numerical method. The problem is, unlike the other solution formulas I've shown you, where I've used this technique before, this cannot be evaluated because we have a solution here, Z of s, that we're trying to solve for. So we cannot evaluate this integral. Okay. So what's done instead? This integral can be approximated, like using a quadrature rule, like the ones I'm about to talk about in 560 in the next class period. Or you can use an idea that I mentioned, actually, last classes, where you replace this by a Taylor series approximation. Maybe even just the first term or something, and at least it's still an approximation. It would be only first order accurate, but it would be something that could be done. So it's not much, but it is a starting point, and there are very effective numerical methods that are based on this idea. It's just a matter of what is done with the integral. So one of my colleagues at University of California, Merced, Maya Tokman, built her career on developing methods from this framework that I later had one of my students use in their work. So pretty cool stuff. Pretty difficult to digest too. So, okay, sorry for a mess, but hopefully I'll get a chance to write this up where I'll fill in intermediate steps here. I should not give homework on this. So honestly, I'll just look at what I've done since the last time I gave homework, which is quite a while ago, and see. I know, probably make it easier on myself too, but okay, well, we'll see. Okay. All right. So, all right, I think we'll call it good. But Taylor, can I talk to you for a couple minutes after we wrap here?
Yes.
Okay. All right, then we're wrapping. Oh, I thought I remember taking pictures of everything. I don't know if I did. That's okay, I did take a picture of my first board. It won't take long.
Okay, cool. I'll send them out. I don't know if you're
Can
gonna.
I see your notes real quick?
Yes,
Okay.
for today.
Yes. Because I want to see if between the first board and the board, if there's something missing. Okay, so, all right, so I did that. Okay, so I did all that. Yep, I got that. And then I can look. Oh, I did get everything. Okay. All right. Did I stop recording?
No.
No, I better stop that. Okay.